for modulating control. Presented by Serge Trudel, Vice President of America Sales, and Ralph Forte, Regional Sales Manager for Control Valves, Actuators, and Accessories. We welcome you to join us for Part 2 this Friday, June 5th, and Part 3 next Wednesday, June 10th. Before I hand it over to Serge, I have a few housekeeping items to cover. First, today's webinar will be available for repeat view after the live session on our website, bray.com. Next, if you have any questions, please feel free to submit them in the Q&A chat, and we will address them at the end of the presentation. And last, this webinar course provides professional development hours credit that meet the technical requirements for a professional engineer in most states. Attendees should verify that this material meets the requirements by the PE board in your particular state, since some state requirements differ.
Americas. I've been on the ISA and also gave classes on ISA on control valves, and I'm part of the API committee. So I'm my world is valves. So if you have any questions afterward, feel free to reach out to me. I'll be available anytime you would need. And my friend Ralph is broadcasting from Idaho, and he's an expert in severe service. He'll tell you all about what he does, and we look forward to helping you today. And Ralph?
Yep. Good morning. My name is Ralph Forte. I've got over 40 years in the valve industry, and just wanted to introduce myself. I do have an extensive control valve background. I have been associated with all three of the major control valve companies in the U.S. So if you have any questions, I should be able to at least get you somewhat of an answer. Thank you.
Great. Thank you, Ralph. So what we'll cover today is the basics of what is a control valve, what is a control loop, which controls the control valve, and the different types of control valves, and also, very importantly, the characteristics of control valves and what they can do, their limitations, where they're best applied, and lastly, the advantages of quarter turn control valves over other style of valves, which is what the point of this webinar is this morning. And we'll have a 10-minute period of questions. We really like to hear your questions, because everybody can gain knowledge with your requests, and feel free. There are only good questions. We look forward to hearing them. That makes our life a lot more fun also. So please don't hesitate to ask anything you would like. So at this point, I'm going to pass it on to Ralph.
So what is a control valve? A control valve basically is a variable orifice in a pipe, and what it must be able to move in order to control. So it's different than just an orifice plate. It needs to have some means of actuation so you can vary the size of the opening, and you must have a pressure drop to initiate flow through a control valve. So there's always a differential pressure if you have flow going through a control valve. And then the control valve is the final control element in the control loop. It's what does all the work. So what's a control loop then? We need to look at what a control loop is, and it's a measurement device, reads some process variable, some condition, either level, pressure, temperature. You're taking in some measurement, and then it's going to a controller, and then you're going to set a desired set point for that measurement in that controller, and then the controller will then communicate with the control valve through control signal. Usually nowadays it's an electronic signal for 20 milliamps, and it adjusts the valve to maintain that set point. So anytime there's a disturbance from the set point, the controller will send a change in signal to the valve to make it adjust its opening to correct the set point. And so valves are controlled in various ways. There's different types of control loops. There's what's called a batch process control. So it's on-off valves typically. They just open and close based on whatever process requires. So if you're making a batch of dough, you open the valve that dumps all the flour in first, and then you open a valve that dumps in the milk, and they're all opened on a timer, and it may be verified by a weigh scale underneath the vessel, and then everything closes and you mix the process. Mixer mixes it. So that's a batch process that's pretty simple. Continuous control is what we'll mostly be talking about, since that's probably 70% of the control loops are continuous control, where there's a measurement variable that's continuously being monitored, and the valve is constantly being adjusted to account for any disturbances away from the set point. So usually it's operated by a positioner, and the positioner moves the valve to make the correction in the process. So again, here's a loop diagram. Basically shows that the valve is the final control element. That's what is doing all the work. You have a measurement device and you have a process controller that are basically monitoring devices, and the valve is the actual control device. So here's a couple of examples of how control loops look. So you have a flow control loop, which you have an orifice plate that's being monitored by a differential pressure transmitter, and that measures the flow through a square root calculation, sends the flow to a controller, and you have a set point for how much flow you want. And every time you have a deviance from that flow that you set in the controller, the signal goes to the control valve to adjust the opening of the valve to make the correction back to the set point. And again, you can see on the right, similar loops with level control as the measurement, and then also pressure control in the lower right. You're measuring and maintaining pressure in the vessel. So original control valves were developed more in a globe style. This goes back into the 1920s and 30s. Originally, they were unbalanced valves, which means the plug had to close against and work against the entire line pressure. So it took a lot of force, the pressure times the area of the plug, to close it. Seeing as they had low air pressure diaphragm actuators, they had to come up with another way to operate larger valves. So what they did was they came up with the balance trim, and the center picture shows you the original globe balance trim. Basically, you had two plugs, and the line pressure worked in opposite directions on both of them. So it's pushing down the area on one while it was pushing up the area on the other, which then negated most of the force required to stroke the valve.
Ralph, would you say that a unbalanced plug design like the first one here is limited to, let's say, a 6-inch size and lower pressure?
It was limited probably to a 2-inch size.
Okay.
The originals were, the unbalanced plugs went to about 2-inch. The double ported balance trim plug globe valves went up to 8-inch, 10-inch. I mean, they made some large ones. It was an excellent control valve. The flow characteristics, it was an excellent control valve, but because it could not load both seats equally, especially if you had thermal transients, it leaked a lot. So usually rated a class 2 shutoff. So people wanted the control valve to do everything. So they wanted it to be a shutoff valve as well. So they came up with a cage-guided trim, which would shut off tighter. And basically, the cage-guided trim, which is all the way on the right, you have holes through the plug so that the pressure, upstream pressure, can go through the plug into the bonnet cavity. And that minimizes the unbalanced pressure that has to overcome the line pressure when you're stroking the valve. And the cage has ports in the sides, so you can see there the flow goes up and then through holes in the cage. So this minimized the amount of force, and they could still maintain large size valves with high thrust requirements with a balanced trim. And then also there are angle globe valves, which were also prevalent for control. You had also had unbalanced, the same as you have in the standard control valves. You had unbalanced trim, and then you also had a cage-guided balanced trim available. These, in a lot of cases, are used on flashing service or erosive service because the outlet is straight shot down the pipe. And you can see on the picture on the right that has a sleeve extended down from the seat ring to protect the body from an erosive media. Rotary valves came about in the late 1960s, 1970s with the advent of Teflon. Prior to that, the rotary valves were mostly lubricated plug valves because that was the only way you could seal a rotary valve. Teflon made a lot of different rotary valve designs possible. So we have butterfly valves. We have double offset butterfly valves. We also have triple offset butterfly valves. We have a V-ball. We have segmented ball valves, and we also have eccentric plug valves. So there's now a whole variety of control valves that are quarter turn. So there's another example of all the different types of quarter turn valves that are available. It makes each one has its own application and has its own characteristic, which we'll discuss in the next few slides.
So also the advantage that I can see here is that regardless of the style of the body of the valve, the actuation is the same. It's all quarter turn, it's all equivalent, it's all interchangeable, correct?
Yep. So globe style control valves and rotary control valves are basically made up of the same components. You have a positioner, you have a pneumatic actuator typically, but it could be an electric actuator. And typically quarter turn valves lend themselves easier to quarter turn electric actuators than linear valves have a much bigger electric actuator typically. So how do the valves actually control the flow? So the valves, control valves, have a clearance. So as you open a valve, you open an area greater and greater to the flow. So the relationship between the stroke and the area that's opened allows your control of the flow. So linear valves typically stroke very short, from like 3/4 of an inch up to maybe 3 1/8 of an inch, whereas quarter turn valves are always 0 to 90 degrees.
So in other words, a 2-inch valve could have a 1/2 inch travel on a globe valve. And all of the stroke or the characteristic is within that 1/2 inch of stroke, as an example.
Typically 2 inches, 1 1/8 inches, I believe. But yeah, it's somewhere in it's shorter than the diameter of the seat.
Right.
So the relationship between how much area is open to flow as you open the valve is called its inherent flow characteristic. So there are several different flow characteristics that control valves have. This first one we're looking at is a fast or quick opening, which means that in a very short percentage of the stroke, you get most of the flow area open to flow your media down the pipe. So in this case, you're looking at a 25% opening of the valve, and you're getting 75% of the possible flow through the valve. So this is good for applications where you need to evacuate or change the process quickly.
Like a relief valve?
Like a relief valve, like
two position open close?
Yep.
Okay.
Another relationship is called linear. So you basically open up an equal percentage of area as the stroke. So if you lift the valve 25% open, or turn it 25% open, you get 25% of this flow. And if you open the valve 75% open, you get 75% of the flow. So the area open to pass the fluid through the valve is exactly the same as what the stroke is. And then the third is equal percentage. So this is a percentage change. So it's a much more precise. You're opening less area to flow. It's a percentage of the previous percent open. So you're getting a much slower, gradual open area to the flow. So this allows for a lot better control on the low end, the smaller percent open. So you can see on the chart, the graph there, it's 70% open. You're still not even 50% of the flow. So
like right. So I think that there's a lot of misconception on the use of those characteristics. I find when customers ask us, I'd like to get a linear valve, what they're actually looking for is a linear process. So controllers work well when the process changes a certain amount and it creates a change of the same percentage amount. And a lot of times, to be able to get a linear system, you have to use an equal percentage valve to create that linear change in process. And that's a little bit misunderstood out there. And that's probably the most important thing to do when you're selecting a control valve, is selecting first the characteristic you're looking for before you even select what type of valves you want, right? Right, Ralph?
Yeah, the installed characteristic is different than the inherent. The inherent is based on area. So it's area open to flow as you open the valve in the trim. That's all just based on area. Flowing characteristic or installed characteristic tends to shift everything if you're looking at the chart, everything to the left. So equal percentage curve will shift and move more towards linear and actual flow conditions, and linear characteristic valves will shift and flow more in a quick opening characteristic in actual flowing conditions.
Right. And I think it's important to note that if you're going to select a control valve to have the lowest possible pressure drop in the system so that you don't absorb a lot of excess energy, then you should look at an equal percentage valve, because that's where it's going to function better. When you're looking at using a linear valve, is usually where most of the pressure drop in the system is absorbed by the valve itself. For instance, if you're using a valve as a bypass to a pump, where you're basically controlling, let's say, the outlet pressure of a pump and bypassing the excess flow that's not required by the system, if you're doing that, then your pressure drop is always constant. So if you're operating a system or a control loop like a bypass valve, which will always have a constant pressure drop through the valve, then your system is really the valve. And at that point, your valve better be linear, because your system is the valve. So your valve needs to be linear for your controller to operate in a linear fashion. But there are very few, or a lot more, opportunities to use an equal percentage characteristic in most control situations, because you're operating with smaller pressure drops and you like to have more control on the bottom end, which is really what the equal percentage characteristic gives you, is a lot of control down here where you wouldn't have had any. Like you said very well, is If you use a linear valve in a system, it'll react more like a quick open. So the first 25% of opening will give you almost full flow. So you're losing the control you think you're getting with a linear valve. And also linear valve have to be cut to the right shape to have a very accurate linear valve. So you're looking at a more expensive valve design if you're looking at a linear versus equal percentage. Does that cover it?
Yeah, I think so. So some valves, the characteristic can be, the inherent characteristic can be manipulated by the trim and the change in area as you stroke the valve. And then there's other valves that have an inherent characteristic by their design, and it's really not changeable. It is what the valve is. It's basically the butterfly valve. There's very little inherent characteristic change you can make. So in the globe valve, the characteristic is on an unbalanced trim. It's the difference in area between the plug and the seat as you open the valve. So you can manipulate that area by shaping the plug. So a quick open obviously is flat. You want fast flow out and no control. Basically, the linear is more of a parabolic plug, and it's giving you a linear change in area as the plug is lifted from the seat. And then the equal percentage again is shaped so that you get a lot less area open to the flow as the plug is stroked upwards to open. In the cage guided balance trim, it's the shape of the windows and the cage. So on a quick opening, you basically have just a rectangular port, and then as you open it, all the flow just flows right through. On a linear, it's a little more of a tapered port on the side. The window is tapered, and then for equal percentage, it's almost a little teardrop V at the bottom to allow minimal area to open as you stroke the valve open. Now we can do the same thing and get the same kind of characterization using a V cut in a ball valve. And the area that's open in a ball valve is very predictable. It's consistent, so you get really good control based on the flow area that's allowed to open as you turn the ball 90 degrees.
And I think you can also create a different shape just about anything you'd like, because you can cut it.
It could be customized to match a flow regime. Yep. So butterfly valve basically has an inherent somewhat equal percentage characteristic. So as it first opens and the disc edge comes out from the seat, you do have a small area open to the flow, but as you turn it further, you're going to get a lot more flow to where it's almost a quick opening. After you get to past 60 degrees open, you're starting to really get a lot of flow. High performance butterfly valve, the same, which is a double offset butterfly valve. You basically have an offset shaft, which is not in the center of the pipe. So you have a little more area opening on one side than the other as you open the valve. So you still get more of an equal percentage initially when you break away from the seat. But then as you open the valve further, you'll get very rapid area open to flow, which will get you more of flow fast at the end. So typically butterfly valves, you want to be controlling 60 to 70 degrees open is probably the range that is the maximum you'd want to control at. Once you get beyond that, you have no control because it's almost a quick open scenario. There's too much area open to control.
Yeah, normally we try to keep it from here to here. And the curve happens to be equal percentage at that area.
Yep. So just a quick review. So fast or quick opening trim design is good for batch processes, which are on-off control, pressure relief, and drains. You want to drain something relatively quickly. Linear is good for fast reactions. You want to make quick flow changes. Typically, if it's a small tank and you're trying to control level, you'd want to have more of a linear. So you want to be able to change so you don't overflow your tank. You change quickly. Pump recirculation, constant pressure drop. It's good in those applications. Equal percentage is usually good for precise control. You're making very small signal change, small changes in flow per signal change from the controller. So you got a lot more control on the process. So if you're trying to add chemicals for pH control, or you want temperature control, and it's typically in a low pressure drop scenario, less than 25% pressure drop. The higher the pressure drop, the more the install characteristic shifts up. So because of the amount of velocity the fluid is going through the trim. So if you're looking at different applications, this is just a basic chart. So for level control, you can use a globe valve or a butterfly valve or double offset or segmented ball valve. V-ball is just overkill. I mean, it's more of equal percentage, and it's designed for more precise control. Temperature control, you can use all the available characterizations are available in all the different styles of valve. Chemical addition, you'd want precise control. You'd want to go with an equal percentage globe valve or a V-ball. Typically, these are small valves anyway, 2-inch and smaller. For pressure control, quarter turn valves, you need to look at a lower pressure drop profile. We'll discuss that on class on Friday, what the reason is for that. But pressure control globe valve is always a good choice, but quarter turn valves will work with low pressure drops. And then flow control, you're just controlling flow, minimal pressure drop. They all work. If you have solids in the line in your process, you have some kind of a slurry, then an angled globe valve is the choice, or we have ceramic trim butterfly valves that will work, and also segmented ball valves work well in those type of processes.
I know we're going to talk about this in more detail when you're doing the second class, but just to define low pressure drop, what we mean by that is a low percentage of the pressure drop of the inlet. So if you're, let's say as an example, your inlet pressure on the control valve is 100 psi. A low pressure drop means to us as a valve company or valve designer is, let's say, like you said, 25% of the inlet. So 30% of the inlet, that's still considered low pressure drop. So it's a percentage always of the inlet. It's not like a definite PSI range, but it's a percentage of what is coming through.
Right. So ISA has a series of classifications for leakage, allowable leakage, and this is on the test bench at the valve factory. So these classifications were accepted for control valves. It's NCFCI 70-2. So people say they want class 6 shut off. That's bubble type, and that's based on bubbles a minute by the diameter of the seat. Class 5 is for metal seated valves typically. Class 6 is typically with soft seated valves. But these are they are allowed to leak on the bench at the manufacturer's test stand. Right. These are the allowable leakage rates. So basically, control valves are allowed to leak.
Right, and bubbles per minute too. So a lot of people think class 6 is bubble tight, but it's bubble tight to a certain amount that's already accepted, and that's brand new valve off the shelf.
Right. So quarter turn valves typically are also sold as isolation valves. So they meet a whole different set of standards for shut-off testing and seat testing at the factory. So you'll find the additional benefit of quarter turn control valves is they're typically tested to block valve standards, and usually if they're soft seated, which majority are soft seated, they will meet API 598, API 60 soft seated, zero leakage at the factory. So you're getting a valve that doesn't leak when it leaves the factory, as opposed to using the control valve FCI classifications where they're actually allowed to leak before they even get to your facility.
One thing's interesting is the last column, the class 6 column only goes to 12 inches. Is there a reason for that, Ralph?
I think
the
that's
standard stops at 12 inches, does it?
Right, the standard stops at 12 inch.
And then everybody extrapolates larger sizes from there, correct?
Right, correct.
So as you can see, it goes up and it's pretty exponential. So imagine a 24-inch control valve, how much it would be allowed to leak. And this is allowed to leak new, and we all know when a valve starts to leak, it just gets worse. But if you start with 0, you have a better chance of staying with 0.
So the title of this presentation was the advantages of rotary control valves over globe style control valves. So this is a good comparison of the two. Globe valves do have their advantages. So globe valves have a low recovery, and we'll discuss what that means in the next class. But in essence, what that means is that globe valves can handle a higher pressure drop. They could also typically can handle a higher temperature because they're typically not soft seated. And then they can also go up to class 4500 if you need that high of a pressure. They also have some trim characteristic flexibility. You saw that the unbalanced plugs and the cages can be taken out and changed, so there's flexibility in the characteristic. If you made a mistake and it's not performing the way you want, if you bought a linear trim cage, you can buy an expensive, but you can buy an equal percentage cage and change it out without having to replace the valve. And they're typically inline maintainable because they have a bolted bonnet, so you can unbolt the bonnet without having to take the body out of the pipe. The cons for globe valves is typically they're much higher cost. They have a lower flow capacity. They have a lower rangeability that comes from both the length of the stroke and then also from the shape of the trim. And then also rising stem valves are harder to seal against fugitive emissions because you're actually pulling the stem out of the packing every time you stroke it. So you're basically taking the stem that's been in the pressure boundary of the valve and is getting exposed to the media and then pulling it out into the atmosphere. Globe valves typically have larger envelope dimensions, so they're much taller and usually heavier. There's more mass to a globe body than a rotary valve body. So they're much heavier, so your piping stresses need to be, and your hangers and everything need to be a little more rigid. And most designs don't have blowout-proof stems because that's not a requirement of ISA to which most globe valves are designed, SP70. And then also, they're typically not fire safe. They're not tested and certified fire safe.
One thing that I noticed we didn't really point out is that because it has a lower capacity, for the same pressure drop, you would have to use a much larger globe valve against a rotary valve. So you can get a lot more flow out of rotary valve, therefore you can use smaller, less expensive valves to do the same job as long as you're within the pressure drop range of the valve you're selecting.
Yeah, typically if you start getting above 4-inch in a globe valve, your cost or price is going to be many times more than a rotary valve. I mean, the price and cost savings difference goes up exponentially as you get bigger and bigger in valve size.
Right.
The rotary valves, like I said, the pros are it's a lower cost solution and it provides a higher capacity because the valves typically have a much higher flow capability, much higher rangeability, because again, we're rotating 90 degrees and we have a much larger area open to flow to control. And then it has a much smaller profile height-wise, typically. Rotary shafts on a rotary valve are easier to seal for fugitive emissions, because the shaft does not come out of the pressure boundary and go back into the pressure boundary to bring out molecules of whatever the flowing fluid is. There's a new standard, API 641, and most of the rotary valves that we have, but most rotary valves are trying to adhere to this new standard for fugitive emissions to minimize any leakage of molecules of hydrocarbon into the atmosphere. We discussed the shutoff. Rotary valves are block valves, shut off. So they're designed to shut off zero leakage from the factory. They typically are, they can be, depending on the valve configuration, but most double offset and ball type rotary control valves can be certified fire safe to API 607. And they also have a blowout proof shaft per API 609. Those are both typically block valve requirements that control valves don't need to adhere to. So globe style valves typically don't adhere to them. And some of the rotary control valves from control valve manufacturers don't adhere to either. So you're getting the benefit of a whole different set of standards in your control valve. And they're designed to function as a block valve, obviously, so they can do both functions in one valve. The cons are on a rotary valve, you have a high recovery, and we'll discuss that in the next class, what that means, but it means you can't take more than 30 to 50% of the upstream pressure in a pressure drop. So what Serge was saying before, if you had 100 PSI upstream, you couldn't drop down to more. If you got close to 50 PSI on your downstream outlet pressure, that would mean you would have some other issues, and we would discuss that in the second class. Because most rotary valves are lower pressure class, ANSI 150 or ASME 150, this class 600. We don't go typically, there are some trunnion design valves that go up to ASME 1500, but most of the time globe valves handle those higher pressures. Can be limited by temperature because rotary valves rely on a polymer seat or an elastomer seat, and we can make metal seated, but those are the exception. In a lot of cases, the polymer elastomer will only go up to like 400 degrees. And most designs must be removed from pipe for maintenance. There are 3-piece ball valves that don't have to be removed from the pipe, but most other designs, we have a top entry triple offset valve that doesn't have to be removed from the pipe, but most of the designs of rotary valves need to be removed for maintenance.
One pro that I think we forgot to talk about was the orientation of the shaft can be, in most cases in rotary valves, can be put in all sorts of different orientations. There are some preferred orientations, but they can actually be fit much easier in a pipe rack or in a very small confined space, so that you can put the valve where it fits best.
Right. So why is control valve selection? Why are we going through this exercise explaining all the different types of control valves and what the characteristics are? Well, one of the reasons is we want to have the most economical solution for the process. So cost is always a consideration, but also controllability. So you want the lowest cost solution, but you also want something that's going to give you good control, since these are the valves that are making you the money. They're controlling your process, which is what your product is. You want something that's going to last a long time in service as well. You don't want to have to be conducting maintenance too often or replacing the valve too often. And it's got to be able to stand up to the demands of the process. And then you can always design a control valve to handle future considerations. So if you're looking at expansion plans 2 years down the road, you can design and select a valve that will be able to handle that future flow rate, hopefully, so you only have to buy the valve once. And then from a safety standpoint, you want valves that are going to maintain your plant safety and process safety. So if it needs to be fire safe or with blowout proof shaft or things like that, you can consider those in the design and what you select. So the least expensive of the rotary control valves is a resiliency to butterfly valve. And they're in a number of many different applications, from HVAC to chilled water to actual water plants for municipal purposes. So butterfly valves probably have a huge population compared to most other control valves because they're so versatile.
You can see the orientation is all over the place in this case, just to suit the application, the location, and there's no way a globe valve would fit in here.
So butterfly valves, we have different types of butterfly valves. So we have the concentric resiliency to butterfly valve. So one of the big benefits of this style of valve is the valve body itself is isolated from the flowing media. So you don't have to go to alloy bodies or any special materials, because the fluid, as long as your elastomer seat matches the fluid chemistry, you don't have to go to alloy bodies to be protected from the process. And then we have the double offset high performance butterfly valve, which is full ASME pressure rated. And that gives you basically a valve that'll fit anywhere the pressure class allows. It also is a Teflon seated valve, but the body is exposed to the media, just like a globe valve or a ball valve. So you need to use different alloy materials based on the chemical makeup of your flow. But both types of butterfly valves offer low cost and easy maintenance. The seats are easily changed. The discs are easily changed. They have high capacity, so which means you can get more flow through them. You may end up with a smaller size valve. Typically, you have the equal percentage flow characteristic, and usually they're stocked in sufficient quantities. You can get quick delivery. So the limitations of butterfly style valves is they're prone to cavitation and noise at higher pressure drops, typically greater than 40% of the upstream pressure. So, and well, like I said, we'll get into more detail on that in the next class. So we're talking about resiliency to butterfly valves. They have a very wide range of seat materials that you can match to your process, and that's why they're prevalent in a lot of water services, seawater service, ultra pure water service. You don't have to use an alloy body because it's protected by this elastomer seat. And then for harsh chemical service, butterfly valves can also be provided with a Teflon, fully Teflon seat and Teflon disc if you get to that point. So you can get a Teflon seat with a Hastelloy disc, or you can get a Teflon seat with a Teflon disc. I mean, on the ASME rated high performance butterfly valves, the materials of construction have to match your process. So you're shutting off full ASME pressures by pressure class. In the case of the double offset, you have typically you have a bubble tight or an API 598 zero leak shut off with a Teflon seat. With a triple offset valve, you get a metal seated zero leakage shut off valve. So again, emphasizing the shut off, you can get zero leakage shut off from the factory in the butterfly valves. Then we have control ball valves. We have two different designs. We have a V-ball, which is a full ball that a V notch is cut with a precise area based on an angle at one end of the cut, and that allows a precise area to open per degree of turn. So it's very accurate. And then we also have a segmented ball valve, which is basically a half a ball, which is supported by a post and a shaft. So it's rigid in its envelope, so it rotates very easily. So in larger sizes, it requires less torque to turn than our V-ball configuration. So the V-ball, it has advantages. Both of them come with different trim configurations. They have a high ratio of high capacity and a high rangeability as well. So you have high capacity, high rangeability, less weight than globe valves. The segmented ball valves can handle an erosive slurry or abrasive service, and they're easy to maintain. And you can modify, you can get different characteristics by changing the degree of cut in the ball. And we can also customize our segmented ball valves as well. Again, we're limited by the differential pressure and temperature. So for the most part, if you still maintain the same less than 40% pressure drop from upstream to downstream, you should be able to use most of the quarter turn valves. Again, here's another configuration. This is this is a fully PFA Teflon coated V-ball, and it all goes into a fully Teflon line body, so that you can get away with not going to an alloy material and save a lot of money.
So the body's ductile iron, correct?
Yep.
Yeah.
So these are the standard, the 15, 30 degree, 60 degree, and 90 degree Vs are the standard configurations for our V-ball. We also can do custom cuts and also a slotted cut depending on what your flow requirements are. The other advantage of using a V-ball is that there's two different body configurations. So ball valves come full port or standard port. So the standard port is a reduced ball size. So typically, if you're sizing a control valve, you usually can go down, because you're taking a pressure drop through the valve, you can usually go down a size in trim and get better control. So this allows you to just select a standard port ball valve and achieve that without having to put pipe reducers and expanders in to go to a smaller size valve. So standard port valves gives you that flexibility. So you basically have an additional set of choices to match your trim to what your flow requirements are.
So if you take these 15 to 90 degrees, you got 4 different V's standard, and then you have a reduced port or a standard port and a full port. So that gives you 8 CDs for valve size, right?
Yes.
Okay.
It works out really well in the largest sizes. So say you had an 8-inch valve that was way oversized, and you didn't want to have to come up with a piping change to put in pipe reducer and expander and put a smaller 6-inch valve in that pipe. You could get an 8-inch standard port ball valve with say a 30 degree V, and you'd have a solution that would work without having to put in all of the reducers and expanders in the pipe and change your piping.
Yeah, and also if your conditions change, then you can just change the ball.
Yes.
Just like a cage guided globe valve, but easier. I went too fast here. That just gives you the curves side by side, right?
That just gives you the curves for each of these. And then this is a view into the segmented ball valve. So it comes with a soft seat, which is a tech-filled PTFE, or you can get it with a metal seat for slurries and slightly higher temperatures.
What's interesting on the segmented ball is that there is no internal cavity like on a regular ball valve, which normally has two seats and then traps the media in the middle. In this case, the segment just turns and closes the opening of the seat, and then there's nothing in between. So it reacts. It's the best of both worlds between a ball valve and a butterfly valve.
And again, the segmented ball valve has got the high rangeability. It's got spline stemmed connection so that it's got low hysteresis. It's a one-piece body. The seat is self-aligning, so it's always making contact with the ball, and it is it's post-guided, unlike a floating ball valve, so that it's got maintenance-free bearings that keep the posts aligned and the shaft aligned.
So at this point, I think it's time for questions. So obviously, Ralph, we've got a three-part series. We wanted to do this in one part, and we both said there's no way. We need to split this up between the theory and then the practice. So we welcome all of you to take part in the part 2, which is Friday. And then there's another one next week as well. So we really appreciated your time listening to us today. And now we're opening up to the questions. So I'm going to ask Jocelyn to let us know if there's anything we'd like to, that the viewers would like to hear about.
Yes, we have a lot of questions in the Q&A. First, thank you, both of you, Serge and Ralph, for an excellent presentation. The first question, does the type of media also play in the decision process?
Absolutely. Go ahead, Ralph.
No, well, we if it's a gas or it's a liquid, and the characteristics of the liquid or the gas play heavily into what you're selecting as a control mechanism. So
yeah. There's abrasion, temperature, solids, what type of solids are going through it.
Compressibility.
Yeah.
Well, on gases, you'll need to compensate the outlet for the volume increase. If you're dropping pressure of a compressible fluid, you get a bigger volume on the outlet, so you may end up with a bigger outlet. So
yeah, very good question. What's the media is the first question.
Yep.
Okay, thank you. Next question, how do you define small pressure drop? If I have a valve with 100 PSI, but pressure drop of say 5%, is this considered small pressure drop? I guess my question is, what percentage of pressure drop is considered small?
So the small, what we talked about is to try to keep the pressure drop, if you're talking about small pressure drops, about 30% or less. Between 30 and 50, you're looking at V-ball application, so that's a percentage of the inlet. So I think that's important, very important in the valve type selection and also on the characteristic selection. So that's what we mean by low pressure drop. When you're looking at anything beyond half of the inlet, you're looking at higher pressure drops and possibly then the more expensive type of control valves.
It depends on what the fluid is. If it's liquid, it depends what the fluid characteristics are, what the vapor pressure is. But then it also depends on if it's a compressible like a gas, how much velocity. Even if you take a 30% pressure drop out of a very compressed gas, say 1,000 psi gas, you're going to get a lot of velocity, and that's another consideration that'll result in noise. So there's a lot of considerations that you need to look at what. I mean, we're just talking rule of thumb. Everything is fluid dependent, so everything has to be analyzed.
First class is rule of thumb. Second class will be the theory, and third class will be how do I do it easy.
Okay, next question. Is rate A better than class VI?
What was that question?
Is rate A better than class VI?
Rate?
What word is that? I still understand.
I'm sorry, I'm not catching the question.
Sorry about that. Is Class A better than Class VI? It says rate.
Is it VI or BI?
VI.
Okay, so he's asking if something's better than Class 6.
Oh, yeah, okay.
So API 598 is better than Class 6, if
Yes.
that was the question.
Yes, by a lot.
And on the soft, that's a soft-seated API 598 test.
Right.
Okay, my apologies. Next question, are the API 641, 598, 607, and 609 standard, or are there incremental costs added to adhere to these standards?
They are all standards that may or may not apply to different manufacturers, but the ones that have that meet those standards do not ask for extra costs for it, except maybe in the case of API 641, which requires a specific type of approved packing. So most API 641 approved manufacturers will use API 6, and I could be wrong on that, API 622 classified packing. So in other words, you have to buy a packing that's already passed the EPA requirements. It makes it easier to pass the API 641 test, but at the same time, ensures to the customer that both the packing has been classified and the valve type with the packing. So some manufacturers may charge more for that style of packing, but a lot of them, like ours, we standardize on it, so it makes it easy to stock one product. And that's probably what most manufacturers will do, so then it doesn't create any more cost as it becomes part of the standard.
The other standards, API 607 fireproof, you have to specify, and it's available in the double offset butterfly valves and triple offset butterfly valves, but not the resiliency to butterfly valves.
Right.
And it is available as a standard on most of the ball valves.
Right.
It's certified to API 607. API 609 is, again, that's a standard. It dictates the lay length, it dictates the blowout proof shaft, so that most of the valves adhere to that, except, again, the resiliency to valves don't meet the API 609 lay length, but they do have, well, depending on the manufacturer, some resiliency to valves have blowout proof shafts, some don't.
And the 607 is, like you said, is an option on the double offset, so that will increase the cost if needed. But on a triple offset, it's inherent, so there's no additional cost for a 607 on the triple offset because it's already metal seated and passed the test as it is.
Right. So that actually the only cost data design is the double offset valve for meet API 607.
Correct.
Okay.
Good questions.
Could we say that a rotary valve could be better on delivery than a globe valve?
I would say most of the time it would be, because rotary valves are mostly used on manual on-off isolation type, and there's probably 10-to-1 isolation valves in the system, so there's a lot more rotary valves being manufactured for block valves. And there's no reason why they cannot be used in control systems if they're applied properly. So good question.
Okay, can a triple offset valve be used for control applications?
Yes, it can. It will have limitations in pressure drop just like the other ones, and will probably function longer because of the metal seat itself will be more resistant over time to the process.
Okay, can you compare operating stiffness of a globe versus butterfly? Which maintains position better with fluctuating line pressures?
That's a very good question. A globe valve gets, an unbalanced globe valve takes all of the pressure on the globe itself, and it has to be completely absorbed by the actuator. So if you change the pressure on a globe valve that's not balanced, it will react to the change in pressure. On a butterfly valve, a concentric butterfly valve has a disc that is balanced basically because it's got the shaft right in the center. So there's a little bit of induced torque. Well, at different velocities, if you're going higher velocities, then you'll have induced torque on the shaft. But things to remember is rotary valves, butterfly valves, ball valve, actuators are sized based on the seating and unseating torque of the valve. And that is usually much, much higher than any dynamic torque induced by the process. So what you have is an actuator that actually is way oversized for the torque at the control range. So the torque actually goes down probably to 30% of the seating unseating torque. So if you've got an actuator that's got a safety factor of, let's say, 25%, and during the control positioning of the valve, you were probably down to 30%. So you've got an actuator that's extremely oversized and a very, very stiff. So it will not let the disc or the ball move at all. Definitely a ball valve don't get affected at all because it actually is in contact with the seat. And it has no torque applied to it based on the flow rate. So a ball valve wouldn't be affected at all. A butterfly valve only in very high velocities. And even then, it's got an actuator that's oversized to keep it in position.
Okay, and due to time, the last question we'll cover in V-port ball valve, how is valve cavity pressure controlled?
In a V-port ball valve, the valve cavity pressure during control, during the control positioning of the valve, the cavity is always in the, it's always partially open, right? So the cavity itself is not self-contained. It's not sealed. So you've got pressure going around the ball, around the edge of the V-ball and inside the cavity. So you see the same pressure in the cavity of the ball as you see inside the line. It's only when you close the valve completely or open the valve completely, then the cavity gets sealed. And at that point, most manufacturers have a drilled ball. So there's a little hole right where the stem goes through, and that little hole then it takes that pressure and brings it inside the body of the ball as well. So it becomes a bigger cavity. And also the seats are normally made to burp downstream or upstream, depending on the valve style. So normally there should not be overpressure in that cavity area, but the process will be there no matter what.
Okay, thank you, Serge and Ralph. Any final comments before we conclude?
Well, I just want to thank everybody for being here today. And if there's anything you need from us, we'll be available anytime. And we appreciate your time.
Yeah, look forward to seeing you again on Friday.
Thank you.
And once again, today's webinar will be available for repeat view on our website.
Thanks.
Enjoy the rest of your day.
Bye.
Bye.